So what we're going to do is look at partial fractions, and I reckon we can get to an understanding of partial fractions by our current understanding of partial fractions. So if we look at something like this, consider the expression 2 on x plus 1 plus 3 on x minus 2. If we were to sort of get common denominators here, you might recall that you need to get the denominators to be common. So you need to multiply x plus 1 by x minus 2, but that means you need to multiply the numerator by x minus 2. And then similarly, you have to multiply 3 by x plus 1. So that would look something like this. Sort of this x minus 2 gets multiplied there, and the x plus 1 gets multiplied over there. So you get something like this. And then obviously now we've got common denominators. So what we can do is we can express that with the common denominator of x plus 1 multiplied by x minus 2. And then what we get is the numerator being, if we expand it, we get 2x minus 4 plus 3x plus 3. And then if we collect like terms, we get 5x minus 1. 2x plus 3x is 5x, minus 4 plus 3 is negative 1. So what we get is this situation here. Okay, what you can see in the denominator is we've got two linear factors. Okay, and what we're going to talk about today is obviously how we go the other way around. So how would we get from something like this to get to something like this? And the reason we need it is because it's hard to integrate things like this, and it's easy to integrate things like this. So we need this to do a lot of integration. So let's see if we can work backwards from here to get back to here. So let's see what that might look like. This is basically what we're going to say. For every linear factor we have in the denominator, we're going to get an expression that has a over one of the linear factors plus b over the other linear factor. Okay. And yeah, if there was three linear factors in the denominator, we would have another one plus c over third linear factor. But in this case, we've just got two. So we get something like this. And then our job is to find a and b. You can clearly see from before that what we're trying to get to is a being 2 and b being 3. So here's what we might do. So what we're going to do is we're going to take this right-hand side, and we're going to do what we did before. We're going to multiply x minus 2 by a and x plus 1 by b. Okay, so you'll get something like this. So a times x minus 2 on the common denominator of x plus 1 times x minus 2 plus b times x plus 1 all over x minus 2 times x plus 1. Hopefully you can see how we got there. And then we're just going to look at the numerator. So I've changed color. Okay, the denominator is always going to stay the same for now. We really want to know what a and b are. So really all we care about is equating the numerators. So let's just ignore the denominator for now, because really all we care about is what a and b are. So we get 5x minus 1 equals, okay, expand the a in. So we get ax minus 2a plus bx plus b. Okay, and then we get let's just bring the x terms together. So we get ax plus bx minus 2a plus b, because what we're going to do now is we're going to take x out as a common factor of this. Take x out, you're left with a plus b minus 2a plus b. So x is a common factor. Now what you need to do is look at it. You need to inspect it, and you need to say to yourself, all right, well, 5 is the coefficient of x. And we can see that a plus b is the coefficient of x on the right-hand side. So a plus b must equal 5. And similarly, this whole thing here, minus 2a plus b, must equal negative 1. So this is what's called equating coefficients. And so now what we have is two simultaneous equations that we need to solve. So what we can do is use substitution to solve the simultaneous equations. So a equals 5 minus b, just fixing that, just sort of rearranging that for a. And then we're going to sub that a into here. So it's going to be minus 2 multiplied by 5 minus b plus b equals negative 1. Expand the brackets, get minus 10 plus 3b. Once you add the like terms, equals negative 1. Add 10 to both sides. Divide by 3, you get b equals 3. Okay, so b equals 3, which is what we said actually. If we look here, b was 3. And obviously a then must be 5 minus b. So a is 2, because 5 minus 3 is 2. So we're here. Okay, so yeah, this sort of stuff on the right-hand side in the colored in color is the steps you need to be able to follow to express express something as a partial fraction, okay? Because you need to be able to integrate. And as I said, these things are easy to integrate. All right, so hopefully that makes sense. Pause it and work it out on pen and paper if you're unsure, because hopefully you can sort of see how that all adds together. Last thing to say is, yeah, it was just a problem I want you to think about and let me know how you go. So the question is express 2x plus 3 over x squared plus 4x plus 3 as partial fractions. Okay, I encourage you to think about how you could what you could do to the denominator to make it more like the previous problem we just did, and then see if you can come up with the appropriate partial fraction decomposition. So yeah, this graph here is not really necessary, but that's what the graph of this thing looks like. So I just wanted to show that, because why not? It's not very relevant to the question though. But later on you might be asked to graph them, so you might be interested in what it looks like. All right, good luck.